Okay, so we're going to get through the rest of the notes here. This is the third example after the Biot-Savart law, and I think this example got a little bit out of order when I was editing the notes, because you don't actually need to use the Biot-Savart law to figure this problem out. The problem is asking us to find the total amount of force on this wire, which is straight in the first section, curved in the middle, and straight again in the third section. So I divided these into 1, 2, 3 sections. And the first section and the third section are easy enough because they're at a perpendicular angle to the magnetic field. If we do IL cross B, I is going to the right. The length is just that length there, R, and then cross with B. So if you point your right fingers to the right and then you curl your fingers up, your thumb will point out of the page. So these two are going to have force that's pointing out of the page. This curved loop is a little trickier because these sections of the curved loop where the wire and the current are parallel to the magnetic field will have no force, and this section here where we're perpendicular is going to have a maximum amount of force, and it changes every little bit along the way. So we can anticipate having to use calculus here. The important thing with this example is to see how the calculus applies, and not so much to be able to recreate every single step on your own, in an FRQ or something. I would doubt that anything like this would ever come up in an FRQ, but it's good to see how you apply the mathematical ideas to this situation. So I'm going to zoom out here and we'll get going. So as we said before, sections 1 and 3 are easy. IL cross B, that cross product just turns into IRB, and that's out of the page, and that's for 2 sections. So we're going to have 2 of those quantities. For the curved section, we write down the version of the force rule, but we use dF and dL because we're talking about a little tiny bit of wire and the little tiny bit of force on that wire. The force is not occurring at point P. The force is occurring at this point. But we are going to end up using point P so that we can relate this little segment dl to an angle. And then we can integrate over this angle from 0 to 180. And that will make this problem a little bit easier. We have to find one index to integrate over. So we have to take dl and write it in terms of d theta so we can integrate from 0 to theta. So when we integrate each side, dF is just going to become the force on section 2. We take our cross product, write it out using the sine function, and arc length, which is dl, is the radius times the angle. That's the basics of radian measurements. When you have gone 1 radian of angular change, you travel a distance of 1 radius. So if your radius is 3 and you go 1 radian, you've gone 3 units along your path. If your radius was 3 and you go 1/2 radian, you go 1.5. You go 1/3 radian, you would go 1 unit. That's all based on radius of 3. So here we substitute dl as our radius times d theta, which is our little angular change here. So our d theta is dl. We're going to integrate from 0 all the way over to pi. Easy enough to do that with a sine function. We get cosine, we evaluate from 0 to pi, and we end up with 2 IBR, which we combine with 2 of these, 1 for the first section, 1 for the third section, and we end up with a total force of 4 IBR, and that points out of the page. All right, so let's finish this off. We're trying to find the net torque on this wire if the axis of rotation is collinear with the straight segments. That means the axis of rotation is this line going left and right on the wire. The first section and the third section are on the axis of rotation, and R is 0 for those. And you can't have torque if R is 0. Your whole cross product ends up being 0. So these don't want to rotate because they can't rotate about a point that's 0 distance away. For section number 2, everything is perpendicular here. Our R's are all this way, and our F's are all out of the page. So our cross product is going to be maximized, and because what we have here is basically a loop of wire, now there's no actual wire on this side of the loop, but if there was wire on this side, it wouldn't contribute to the torque because, again, it's on the axis. So we can take our result from page 7 and we can use that the torque is IA cross B, where A is the area of this loop, even though it's not a loop. Remember, this side does not contribute to the torque. That's like the example we did on page 7, where the axis of rotation was one of the edges of the rectangular loop. Go back and look at page 7, okay, and familiarize yourself with that again. So cross product gets maximized. We're at 90 degrees between our area and our magnetic field. The area of this is pi r squared over 2. And so we get our net torque to be pi I r squared b over 2. All right, on the next page, we're going to start looking at Ampere's law. So the big idea behind Ampere's law is that the magnetic field in the area around a wire is proportional to the amount of current that's enclosed. So you take any path you want around some amount of current. You could have 2 wires, as is shown as this example. You could have 1, it doesn't really matter. But whenever you make a loop around a current, the dot product of the magnetic field and the path that you take is going to be proportional to the current. More current, greater magnetic field. Less current, smaller magnetic field. And using Ampere's law is going to rely heavily on symmetry, just like using Gauss's law relied heavily on symmetry. So the integral form is the line integral of the magnetic field. Dot product with your little line element is mu naught times the enclosed current. This is a line integral. It looks the same as a surface integral. We talked a little bit about line integrals last semester in mechanics. And we can know the difference between a line integral and a surface integral by looking here. dl, that's for a line. dA would be for an area integral. And with line integrals, you can choose any path you want, but you have to make a closed loop. So if I start here, I got to go back around and I got to end here. But how I do that is up to me. I could go way out to the right and come back. I could cut in close. I could take a square path, a circular path. It doesn't matter, octagon, whatever, as long as I end back at the same point that I started. So I know this is maybe a bit hard to understand at this point. But I think after you see some examples, you'll get the hang of this. And these drawings up here make this idea seem perhaps more confusing than it is, because you got 2 wires and the shape of this path is funny. Remember, this is going to be used in highly symmetric situations, and we take advantage of that symmetry, and it's going to be a little easier to understand. So hang in there, and we'll talk more about this in class. All right, so at the bottom of the page, we got one more little right-hand trick that we can use, and that is if you point your thumb in the direction of current, which in this case is up, your fingers will curl in the direction of the magnetic field that's created. So this straight line is the current, and this one that's circling around is the magnetic field that's created by that current. All right, so we're on the next page here, and we're trying to find the magnetic field at some distance away, r, from this wire, which is carrying current to the right. And by using that extra right-hand trick, if you point your finger to the right and curl your fingers, they will be coming out of the page at you. So up at the top here, this B vector would be our magnetic field. That's coming out of the page, and our little element DL would be coming out of the page. Down here, B would be going down, DL would be going down. Here, B would be going back into the page, so would DL. Over here, B would be going up, so would DL. So DL and B are parallel at all points on this loop. That makes taking our dot product very easy, and this is a very symmetric situation. We have one wire. Our Amperian loop is centered on that wire at an equal distance away. We have kind of circular symmetry that we're dealing with here. So let's go and look at how you would actually apply Ampere's law in this situation. It ends up being a pretty nice, elegant, easy way of doing things. We start off with Ampere's law. The line integral of B dot dl, and we know it's a line integral again from L. If it had an A, it would be an area integral. That's equal to mu naught times I enclosed. Because this dot product is maximized because of our parallel nature of B and DL, they're always at 0 degrees to each other. This is a constant, it factors out. This is the length of our loop, which is just the circumference, 2 pi r. Now we just divide and we get B. B is mu naught I over 2 pi r, which is a result that we've already got from our previous work, but it took a lot of integrating to get there. This, much faster, much more elegant. Okay, so we're going to look at wires that exert forces on each other. We have a very long wire, and then we have a section of wire here some distance away. And we're going to find the force on one wire or the other. It doesn't really matter which way you do this. I'll find the force on this top wire. We know since forces occur in pairs, the force on the bottom wire would be the same. So the bottom wire here creates a magnetic field that points out of the page in the vicinity of the first wire. If you point your thumb to the right on I2 and curl your fingers, that will show you the direction of the magnetic field from I2. So you point your thumb to the right, curl your fingers, and they come out of the page up here. Then we can do QV cross B for this. So V is to the right, or IL cross B. I is to the right, so you'd want to point your right fingers to the right and curl them in the direction of B, which is out of the page. And when you do that, your thumb points down. So there's a downwards force on wire 1. That's an attractive force. There would also be an equal and opposite upwards force on wire 2. Now, what's the magnitude of that force going to be? Well, the magnitude of this magnetic field here is mu naught I over 2 pi r. We just got that result. And we know force is IL cross B. The cross product is maximized because they're at 90 degrees. All we really need to do then is substitute in for B, and we get our expression for the force. Notice that it's proportional to each of the currents. So you double both currents, your force goes up by 4 times. And it's inversely proportional to the distance between them. So the couple of bottom questions here, you get to fill those in on your own. When is the force between two wires attractive or repulsive? Well, we can see it's attractive here when they're going in the same direction. if we turned one of these wires around and the current went the other way, the force would go the other direction, and then it would be repulsive. So if the wires have current flowing in the same direction, they're attractive force between them. If they go in opposite directions, repulsive force. And when do they carry current but don't exert force on each other? That would be when they are perpendicular. If they are perpendicular, then the cross product will become zero. All right, so we're going to look at the magnetic field inside of a cylindrical solenoid. A solenoid is a whole bunch of loops of wire, almost like a slinky, right, that have current going through them. And they create a nearly uniform magnetic field on the inside of this. Here's the magnetic field just from one loop, and you can see how it's pretty much straight on the inside. And then when you add in all the other loops that would be next to this, any of these curvatures here, they get canceled out. And you have a uniform magnetic field on the inside of this, just like there's a uniform electric field inside of a capacitor when it's charged. So we're going to use an Amperian surface here. And let's look at some conditions here. Okay. One important thing is to assume the magnetic field outside the coil is very close to zero. So we can ignore any magnetic effects up here. And our surface that we're going to use is this kind of rectangular surface here. It goes through point P, and it's equal distance down and up. So we have symmetry and everything. The magnetic field is pointing to the left in this case. And when we go to take our path integral for our Amperian loop, let's say we start at point P and we go to the left. Now this section of wire, the magnetic field points left, our little line elements would point left, so the dot product is maximized. In this section, when we go up, the magnetic field is still going left, but we're going up. That's at a 90-degree angle. So the dot product there vanishes. The top section of our loop contributes nothing because the magnetic field is zero. So when you take a dot product, you get zero. And the right section coming back down, same as the left. Our DL is perpendicular to our magnetic field, so dot product zero. And then coming back in, this section, our magnetic field and our DL elements are in line with each other, so the dot product is maximized. So there's really only one of the four sides that contributes to the overall integral when we do our Amperian loop. So let's take a look at some of the details of this, and I wrote down some words to go with it that help to reinforce some of what we just said. So we integrate on the dotted path. There are n number of turns within that loop, and each individual loop has a current I going through it. This path and this path, portion of the path, are perpendicular, so the dot product becomes zero. On the top, the magnetic field is small. We ignore it. It's basically zero, so the dot product is zero. Only the bottom part here contributes to the line integral, and it's a very easy line integral to do. Since the dot product is maximized, we just multiply L times B for our line integral. So we have the line integral of B dot dl equals mu naught times I enclosed. This line integral just becomes B times L. And since we have n loops of wire in here, right? We had n of these things. We take for our current enclosed n times I, because I was the current per loop and n was the number of loops. So we get a magnetic field of mu naught Ni over L. So if you have a solenoid and you want to make the biggest magnetic field possible, look at what you need to do. You need to have a high number of loops. You need to have a high current, but you want a short length. Basically, you want the maximum number of loops per unit length. So more turns is better and more current is better for creating a large magnetic field inside a solenoid. And the last example on this page is of a toroid. A toroid is just a solenoid that's in a loop. Right? You're using loops to make a loop. I don't know whose loopy idea that was. Anyways, we have n total turns going around our loop. And the really only difference between what we just did a moment ago and now is that our length, instead of just being L, is going to be our circumference, which we express in terms of the radius. This little trick with the current enclosed still works. We have n turns, each one's carrying a current I. We divide and we get the magnetic field mu naught Ni over 2 pi r. So if you wanted to make a toroid stronger, you would decrease the radius, keeping other things equal, and of course, increasing the number of turns, increasing the current will also lead to a greater magnetic field. All right, so we're on the next page, last page, and we are looking at a wire of radius r with a uniform current flowing through it. And we want to use Ampere's law to determine the magnetic field outside of the wire and inside the wire. Outside the wire is going to be easy because we've already done this a couple times. We have our circular Amperian loop there, centered on the center of the wire. We take the line integral of b dot dl equals mu naught I enclosed. The current enclosed is just I because our entire wire is enclosed. Our Amperian loop is going to have a circumference of 2 pi r. That's the distance around the loop. And we divide and we get b equals mu naught I over 2 pi r, which we've already seen this result a bunch, but it's so popular. Get used to it. This is, just like using Gauss's law to find the magnetic field outside to find the electric field outside a charged conducting shell or something like that. The second part of this question becomes a little harder because now we are trying to find the magnetic field inside the wire. And inside the wire, we have to think about the amount of current that's enclosed and not the amount of current that's outside of it. So to do that, we're going to use a current density. Current density would be the current per unit area. Since the current is uniform in here, 1 square centimeter over here is the same as 1 square centimeter over there, or square millimeter or whatever. They're always going to have the same amount of current going through it. So we measure current per meter squared. And the cross-sectional area here is pi r squared. So our current that's enclosed in our tiny circle inside the wire becomes our current density times the area of this little circle. And the area of the little circle is pi little r squared, which is different than pi big R squared, right? Big R is to the edge there. When we do our Amperian loop, all the same little tricks apply. B is constant, we bring it out. The dot product gets maximized because B and DL are always in the same direction. The length is the circumference, 2 pi r. We already found what I enclosed was. We divide and we end up with this. The magnetic field is still linear as you move out from the center. So the most complex part of this one was the current density part, finding out how much of your current is enclosed there. All right, let's move on. Okay, so now we're looking at a coaxial wire. A coaxial wire has a wire in the center, an insulating section, and then another wire around it, and there would be some sort of insulation on the outside of that. This is oftentimes used for communications, used in televisions, like the old way the television's plugged into the wall, or still, I guess, the current way that a lot of them do. So we've got current flowing this way on the inside wire. It's flowing the opposite direction on the outside wire. I've defined that the current that's going in, which is kind of the outside one, to be negative, and coming out is going to be positive. That's just my choice. You could do it the other way if you want. So when we go to apply Ampere's law here, it ends up being pretty straightforward for the first two sections, right? We've already done these ones before, and so we can just take our results from above, right? We had inside this little tiny wire, we take this result and apply it. In between the two wires, the outside wire contributes nothing since it's not enclosed current. So we take our result from part one. For the next section, though, when we're between B and R and C, this gets a little tricky because now we're going to be inside the second wire and we want to find the magnetic field, and we need to know what the current enclosed is. So I'm going to zoom in and we'll take a closer look at this. Okay, so in this region here, between B and C, which is what we're looking for in our next part, what's the field going to be in here? We have to figure out the current enclosed. The current that's going into the page here, which would be negative. So this in here is not the current enclosed. That's the current going into the page. To find the current that's totally enclosed, we would take the amount that's going into the page, which would be negative, and we would add to it this current, which would be positive. Okay, so be clear. This is not the total current that's enclosed. This is the amount of current that's enclosed just in this outer shell. So say we're halfway through this outer shell. That's how much current is in the first half of the outer shell. And it does not include the current from the very middle. So the current that's flowing into the paper at our radius is I, which is the total current. And then we have to use some proportions here. So when you think about this, what we need to do is take the amount of area that our little kind of a hoop incorporates, and we need to divide that by the total amount of area in this outer surface, this outer hollow disc, whatever you want to call it, right? So the amount of area that we're going to have is our radius, R, which would be somewhere between these two lines. So pi r squared tells us that area, and then we subtract away all of this area here in the middle, which is empty. And then the total area for this outside disk is pi times c squared, which is the outer circle, minus pi b squared, which is the inner circle. So what we have is our area divided by the total area of this outer washer kind of cross-section wire. Now when we apply that with Ampere's law, our enclosed current is the current going out, which is positive, minus the current going in, which was negative. This process works out pretty simply, but it seems more complex than it is just because of this current business. Don't let all these, details distract you. Our integral of B dot dl is going to be mu naught times I enclosed. The enclosed current, we just found that. B dot dl is just going to be 2 pi r. And so we divide that over to the other side. And the actual application of Ampere's law here works out very easily, but the stuff with the current can be a little tricky till you get the hang of it. Lastly, when we are at a radius outside of the outer wire, our enclosed current is 0 because we had I going in and we had I coming out, and so no magnetic field on the outside. Thanks, and we'll see you in class.